Hi Dhananjay. Hello, hello, hello. Hi Dhananjay.
Hello.
Hello.
Sir, I have one doubt in the last week discussion.
Class week 8 discussion.
Yes, week 8,
Okay, which topic?
question number 5, sir.
Question number 5 in week 8. The discussion I have done or regarding your assignment.
Doubt in how you calculate the maximum saturated point.
Maximum?
Saturated point. First, final values.
Okay, final values in which I have discussed or regarding your assignment. Fifth question,
Yes.
which I have discussed.
Yes, I have doubt in that final value.
No, that is what I am asking. The question number 5, I have discussed the question number 5 of your assignment.
Yes, question number 5 in your regular class. In your week 8 discussion class.
Okay. So can we
Yes.
discuss
Not in
after?
assignment.
Can we discuss after the class because it's better to start the class.
Okay.
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 So good evening everyone. Today is week 9 discussion of this course Vision, and this course is taken by Professor Jayanta Mukhopadhyay, Professor Computer Science and Engineering Department of IIT Kharagpur. Myself, Ayan Paul. I am a PMRF Research Scholar of IIT Kharagpur and I am a TA of this course. By TA, I will my duty is to discuss some of the question that will be very much similar to your assignment, so that whenever you will solve your assignment, you will not feel it's a completely new, or it will be much easier for you. But before that, I always prefer to first discuss regarding some of the concepts or summary of the week, and then we will move on to the question answer. Okay, so yeah. So this week we will discuss something about range data. Previous week we have discussed regarding colors. Okay. This week we will discuss something about range data. So what is this range data or range image? A range image is a spatial type of image in which each pixel value does not represent brightness or color, but rather distance range from the sensor to the surface of an object in the scene. Okay, so that is range image. Means earlier whenever we are talking about conventional image, the pixel value, that is the xy value, that gave the intensity or the color values. Like you have seen, like in a 8-bit image or 2 to the power 8, that is 256, means the color values will be between 0 to 255, right? And then we have this three different channel RGB, so that is why three different value of R, G and B, all from 0 to 255. That is regarding our conventional image. But when we talk about this range image that we will be discussing today, in which each pixel will give us the depth, okay, that is distance from the viewpoint. That is why this type of image is known as 2 half D image. Okay, not exactly 3D image but 2 half D image. Okay, why 2 half D image and not 3D image? 3D image means both x, y as well as z. That means both your intensity, xy intensity, as well as the depth. But when we talk about the range data, in here we are talking about only depth, okay, and not the intensity as well as depth. That is why it is known as 2 half D image. Okay, rather not 3D image. 3D image means all, that means x, y as well as the color or the intensity, x, y, z as well as the color intensity value. Okay, z will give the depth coordinate and x, y will give the color. So that is 3D image. But range image means is a 2 half D image. That means x, y will only give me the depth. Okay, and the x, y will only give me the depth. Okay, so that is why it is known as range image or range data, and also it is known as 2 half D image. Okay, so an image Dij which records the distance d, okay, to the corresponding scene x, y, z for each image pixel ij. Okay, for each image pixel ij it will only detect the depth. Okay, earlier for each image pixel ij in conventional image it is only detecting the intensity or the color values. Okay, so this is the difference between your conventional image and this range image. And there is another thing that is known as 3D image. There it has all, like x, y, z as well as x, y will represent the color, z will represent the depth. So that is a 3D image. Okay, so it could be provided as a set of 3D scene points or the point cloud. So this is actually, this is the range image. Okay, this is you can say normal conventional image, but yeah, if it has a depth, we can call it a 3D image. Otherwise this picture, this is your actual range image. Okay, so this is regarding range image. Now what are the techniques by which we can get the range image? So there are two you can say two types of technique. One is called as passive imaging technique, and another one is called as active range imaging. Okay, so what is this passive range imaging or active range imaging? So passive range imaging, it extracts depth information without projecting the energy into the scene. Okay, so like stereo imaging all we already have seen. Like we will place in instead of one camera will only give us x and y. But if we, okay, someone is joining, yeah, one camera will only give us x and y. That yeah, that is regarding a normal camera. But if we are talking about stereo imaging we already have read, right? Like one is will be the right camera, one will be the, or one will be the left camera, one will be the right camera, right? And from this two image we are extracting the depth. Okay, so that is stereo imaging. Okay, so the difference in this is known as passive range imaging technique. Okay, why passive? Because it extracts the depth information without projecting any energy into the scene. Okay, that means the camera that the two camera we are using in the stereo imaging, that is not projecting any energy to the scene. Okay, rather we are just collecting from one camera, we are collecting one scene, from second camera we are collecting the same scene, and then by that we are calculating the depth. Okay, so that is passive range imaging. Another thing known as active range imaging. What is this active range imaging? Actively projects energy, light, laser, or infrared, IR means infrared, okay, onto the scene and measures the reflection and compute its depth. Okay, that means here in active range imaging, the camera or whatever the source that we have, that will project energy onto the scene. Okay, earlier in passive imaging we are not projecting any energy. Okay, we are only taking energy from whatever light we have. Okay, but in active range sensing we are projecting energy of its own. Okay, so that is known as active range sensing. There are three types of active range sensing. One is time of flight sensor, second is this triangulation based sensor, and third is the structured light. Okay, so what is this time of flight? First is time of flight. So time of flight, we use a laser. Okay, laser or lidar, whatever. So laser generally we use. Laser means laser sensor. So what is this lidar is light detection and ranging. Okay, for lidar we lidar is, yeah, light detection and ranging. Okay, so what is this what is the we generally use laser in light detection and ranging. So what is this laser does is it projects the energy, okay, it projects the energy onto the object, and then what will happen if we project this energy onto this object? We want to know the depth of this object, okay, so we will just project the energy into this object, and after reflecting it, we will again collect the energy back, okay. So why we are doing this? We are doing this to calculate the distance. How we can calculate the distance? We know the speed, okay. Speed is nothing but distance by time, okay, d by time, that is speed, okay. So this is the thing, this speed is known as speed equals to distance by time. But here you can see there is two distance, right? One, when the laser is going from this source to the object, and second, when the laser is reflected back from this object to the source, okay. So that is why we have this 2d distance. We don't have this d distance but 2d distance. From this we can easily get the d will be t into v by 2. So by this we can calculate the distance of the object. So this technique is known as time of flight range sensor, okay. So this is the first technique for this active range sensing. Similarly, we have this method known as triangulation based sensor, okay. Now triangulation based sensor, in triangulation based sensor we have this three thing. One is the light source, second is the object, this is nothing but object, and third we have this camera, okay. So what this do is it is based on the triangulation method, because we have this three things, okay. One is the light source. Someone is joining. Yeah, one is the light source, second is the object, and third is the camera, okay. So a very layman if I say, the light source will be going, and it will be interacting on the from the object, and this interaction will be captured on the camera, okay. So that is known as triangulation based sensor, okay. So earlier in this time of flight we have this same emitter as well as the receiver, or same emitter and receiver, but here we have this emitter in the form of this light source, but receiver in the form of one camera, okay. So this is the difference between your, okay, someone is joining. Yeah, this is the difference between your time of flight and the triangulation based sensor, okay. Now we have this structured light. It is very similar. This triangulation based sensor and this structured light is very similar, but it is an advanced form. What difference here? See, here we are projecting only a beam of light, right? But now what we will do, we will project a you can say a strip of light, okay. That is why it is known as structured light, and we will collect the same strip from on this camera. Previously we are only collecting a beam of light, or a point of light, okay. But here we are projecting a structured you can say structured light, or better you can say a line or strip of light, and then we are collecting the same line or strip of light. So this is known as structured light. Now there are different technique of encoding, okay. So we have this generally two type of encoding. One is this binary encoding, and second one is this space encoding. The space encoding can be in the form of strips. The space encoding can also be in the form of this patterns. But space encoding, okay, so let me show you the difference, that will be better. So one is the space encoding or spatial codification, and second we have this binary coding, okay. So encoding here, it is a spatial, that is single pattern, okay. Like you can see here, this is also single pattern, and this is also some kind of single pattern in the form of line or in the form of dot. So that is why it is spatial, okay. But binary, we have this temporal or multiple patterns, okay. Multiple patterns, you can see pattern 1, pattern 2, pattern 3, okay. So different type of patterns. So this is one difference. Then pattern type, in this spatial coding we either have this color strips that you can see in the first image, we have this color strip, or we can have this dots, okay. So that is regarding the spatial encoding, okay. But in this binary encoding, we have this binary gray coded strip sequence, okay. So this is the difference. Second, in this spatial encoding we have only one frame needed, but in binary encoding we have many frames. This is one frame, this is one frame, this is one frame, so many frames needed. Okay, so accuracy, what is the, why we are doing this binary coding instead of this space encoding? That is because to achieve a higher accuracy. Here the accuracy will be moderate, but here the accuracy will be high. Okay, as the accuracy is high, it is actually slower because it have to capture multiple frame. But here, as the accuracy is moderate, so it is very fast. Okay, so it is best for actually moving object, because there we required much faster speed to process. But here it is better for static object and high precision scanning. So these are the three type of encoding that we do for this structured light. Okay, structured light. So this is the thing. This is the thing regarding coding strategies. Now this RGB images from Microsoft Kinect. So it is a type of this same thing. It is a type of this structured light. Okay, so one camera based on this structured light. Okay, so RGB images from this Microsoft Kinect. This is the actual scene, and this is the range image data you can see. So it uses a infrared laser light with speckle pattern. Okay, so this is the thing. Now why we are using laser, that should be the question. All these are theory part, but still it's better to know. So easily generate bright beams with lightweight sources. So the sources, if we are using laser, the sources used for projecting the laser, that is actually lightweight sources, but other sources are actually heavy, so we go with this laser. Second, infrared beams uses unobtrusively focus well on this given narrow beam, so all you can read. So this is important, focus well on narrow beam. And second, this is a very important, that is easily generate bright beams with lightweight sources. Okay, so that is why we generally use for this lasers. The source that we are using, that is actually most of the cases, that is laser light. And this is again, I have given the differences between time of flight, triangulation and structural light. So you can read the definition or principle I have already told you. Range generally for time of flight, for this long ranges, when we require this long ranges, we use this time of flight. For example, whenever we are taking any scanning of this inside the sea or something, we generally use this sea, or whenever we require this long distance, we go for this time of flight. Triangulation, it is short. Okay, and structural light, it is kind of in between this time of flight and triangulation. Okay, accuracy, it is medium to high. Triangulation, it is as a very high accuracy, because we are only dealing with on a short range. Okay, that is why it has this very high accuracy. And here it is kind of medium. Okay, speed, it is a fast real time possible. It is slower. Triangulation, it is slower, it depends on the scanning. And medium, it needs the pattern. And there are different there are different examples. You can see example of this time of flight. One, lidar, I have already told you. Structured light, I have already told you, like this Microsoft Kinect, it is a structured light. Okay, and then environment and etc. You can just read. So basically, in the first two slide, what we have studied, first two slide or first three slide, what is a range data or range image, how it is different from a conventional image. Okay, so again I am repeating in short. Range, conventional image, we have this pixel, and this pixel gives us only intensity or color values. Okay, but whenever we are talking about range image, the pixel does not give the color value, but rather it gives the depth value or distance from the viewpoint. Okay, so that is the difference between the conventional image and the range image. That is why range image is also known as 2 half D image. Why 2 half D image? Because 2 pixel will only give us the depth. Okay, that is why 2 half D image. Now there are different techniques to have the range imaging. One is passive range imaging, and second is active range imaging. Passive range imaging we already have studied, like stereo imaging. We know stereo imaging. If we keep two camera, right camera, left camera, and right camera, from this two camera, if we see the same scene, we can get the depth of the scene. Okay, so that is stereo imaging. And then we have this three active range sensing. One is this time of flight, okay, that generally use laser. Second is this triangulation based sensor. Okay, triangulation based sensor means three things we require. One is the light source, and there is the camera, and third is definitely the object. Structure light very similar to triangulation based sensor, only here we are only using a beam, or only using a single beam. Here the beam we are using is large to get a pattern, okay, to get a pattern, and that pattern is observed by this camera. Okay, so that is the difference between triangulation based sensor and this structure light. Okay, and then there are different types of encoding, and then this is an example of the structure light, and this is the comparison. Okay, so this is regarding a broader view, or you can say general view of the range imaging. Okay, so is that, are the things clear to all of you? Any doubt in this? Any doubt in this? Am I audible? Am I audible? Hello?
Yes, sir.
I
Yes,
have a
sir.
question here.
Yeah.
Uh, yeah, so if I capture the same image using three different range techniques,
Yeah.
so how can I identify that this image is captured using different range techniques?
How you can identify? No, it will give the same depth value that you cannot identify, but based on the accuracy, speed, accuracy you can confirm. Like if it is very accurate, then definitely it is from a short distance, and then we are using mostly the triangulation method. Okay, if like time of flight, accuracy will be low, so from that you can understand. But it will give the same depth, right? Because here depth is the only thing to concern about.
Okay, so there is no way to classify whether the image is captured from lidar or if it is called if it is captured through triangulation. I
No,
cannot classify.
there is no like lidar and like lidar and any 3D scanner like lidar, or like there is a 3D RGBD camera generally used this that is known as this Intel Real Sense camera. So you cannot detect. Okay, see, both will give you the same point cloud, lidar or this RGBD sensors. Okay, it will give the same point cloud, so that you cannot classify. But
Oh,
yeah, but see, lidar, it will only give you a point cloud, like and if you have this this days you have this advanced sensor, so they will give you RGBD image. Okay, so that is 3D image. But this lidar is, it is only a 2 half D image, that is only a range image, so that can be a difference. Okay, but otherwise you cannot predict the difference.
okay, got it. Thank you.
So everyone understood, right? What is the difference between the conventional image and this range image? At least this part it should be very much clear to all of you. What is the difference between a 2D image, 3D image, and 2 half D image? Is it clear? 2D, 3D, and 2 half D? Clear, right? 2D is a normal image that will only give you a pixel value, will only give you a color intensity. 3D, it is RGBD, that means XYZ value, that is XY is color and Z is your depth, that is a RGBD. Okay, and range is in between, that is XY value will not give you color, but XY value will give you the depth. Okay, so that is the range image. So this is the three difference. This is the difference between these three things. Okay, and range imaging, we are using either passive range imaging or active range imaging. Active range imaging means emitting the energy and then collecting it. Okay, so that is passive range imaging, or rather you can say we are projecting our own energy, so that is active. Passive means we are not projecting any own energy, we are only using the energy from the environment, that is the light around it. Okay, so that is the difference. Okay, so let me move. Okay, so parametric curve. So we have this 2D and 3D parametric curve. Okay, so 2D and 3D parametric curve. So what is this parametric curve? Parametric curve means we are using a parameter, okay, to understand the curve. Okay, so here 2D parametric curve, that means we have this by this one parameter, that is t. Okay, parametric curve means we are using one parameter, so that here we are using t as a parameter. So by this one parameter we are making this two things, okay, that is x and y coordinate, you can say. So this ut is x coordinate, vt is y coordinate, and parametric 3D curve, so that is why we are using r to r square. R is nothing but the parameter, that is t, okay, and r2 means this ut, or u as a function of t and v as a function of t, okay. And in 3D curve, if I compare 3D curve, so we write it as r2 r cube, or r2 r cube, yeah, r2 r cube. So r2 r cube means, r means we are again using the same parameter, or single parameter, that is t, and we have this 3 coordinate, that is u as a function of t, v as a function of t, and w as a function of t. Okay, so that is regarding the equation of the parametric curve in 2D as well as 3D form. Okay, second point is tangent. Tangent is very easy. Tangent is nothing but a single differentiation of the curve. Okay, that is d by dt, or d by del by del t, not del means partial, so d by dt x t. Okay, so that is tangent. Okay, so nothing, you have to just differentiate it, so that is why it is written as u dash t and v dash t, single differentiation. Tangent to this point in this 3D parametric curve, again it is a single differentiation, so ut will become u dash t, vt v dash t, and wt w dash t. Okay, and next we have this curvature of a curvature at a point. So tangent at a point, it is very much clear, and then we have this curvature at a point. Okay, now curvature at a point, curvature is given by this equation. Okay, that is x dash cross x double dash mod of this divided by x dash cube mod of this cube. Okay, so that is curvature at a point. That means first from this xt you have to calculate x dash, then you have to calculate x double dash, then you have to make the cross product of this two, and after that whatever the result you are obtaining, you have to do the mod of it, and then you have to divide by x dash mod, and then you have to cube it. Okay, so that is curvature at a point. So what we understand from the parametric curve, so this is nothing but a point xt given by ut vt. Similarly, I am not same thing, 3D curve means only one coordinate we are that is extra. Okay, here we have only uv, here uvw. Okay, so that is the only difference. And why parametric? Because we are using this parametric t, parameter t. Okay, that is why u is written as a function of t. Similarly, v is written as a function of t. And then tangent is single differentiation, or x dash t. It is very easy, that is u dash t v dash t. And then you have this curvature that is given by this equation. Okay, so this is the thing. Then we have this thing. There are different, you can say there are different planes associated to different thing. One is this tangent that we have already discussed. There is another thing, that is normal. Normal is nothing but the normal to the tangent. Okay, so that is normal. So one is tangent, and there is normal, and second is binormal. Okay, so that is given by b. Okay, so tangent t, b, and t, v, and we write as n. Okay, these are the three things, t, v, and n. How we now by these three things we have this three different plane. One is known as binormal plane, another one is known as osculating plane, and another one is known as rectifying plane. So what is this binormal plane? Binormal plane is the plane that is made from bt and tt. That means binormal and this tangent. Okay, so that is known as binormal plane. And second, we have this normal plane that is made by this nt and bt, that means normal and this binormal. And then we have this osculating plane that is made from this tt and this, yeah, TT and NT, okay, that is tangent and normal. And rectifying plane, this is binormal. Okay, this is binormal. This is yeah, sorry, three plane: normal plane, rectifying plane, and osculating plane. So rectifying plane is this plane that is made by BT and TT. Osculating plane is this plane that is made by this TT and NT, and this normal plane that is made by NT and BT. Okay, so these are the three planes from this terminologies. Okay, three different planes. And then we have this three things. This is known as tangent equation, and then we have something called normal equation, and then we have this normal equation. Okay, so tangent, you can say it is a change in curve, or a change in direction rather. By tangent it is torsion, and anti, that is normal, that is given by this combination of tangent and bitangent. Okay, so only these things you have to remember. There are three different plane, and which plane is formed by which vectors. Okay, which vectors, so that you have to understand. Other things are generally, this quotient does not come from this formulas. Okay, so this is the theory. And then you have this parametric surfaces, that is very important. So parametric surfaces means here in parametric curve we are using only one parameter, that is t. But here in parametric surfaces we will be using, instead of one parameter t, we will be using two parameter, that is uv. So that is why our point x, y, z will be written as x as a parameter uv, y as a parameter uv, and z as a parameter uv. And this uv can also be written as a function of t. Okay, so that is why it is known as parametric surfaces. Earlier we are using r2 r2, or rather r2 r cube. Okay, that means one parameter to 3 points. Here it is r2 to r3, that means two parameter uv to this 3 points or 3 coordinates. So that is the parametric surface. Okay, and for parametric surface, this is how we are writing the normal equation, normal to the curve. Okay, that is x u cross xv divided by mod of this xu into xv. Okay, what is this xu? Xu is nothing but del x by del u. Okay, that means partial differentiation of x with respect to u. And del similarly xv, that is del x by del v. And others you can just do the cross product and take the mod of it. So that is how we are writing the normals or surface normal equation. Okay, so this is the thing. So what you have to understand, there is a parametric curve that is only taking one parameter, and parametric surface. Okay, parametric surface will take two parameters. Parametric curve will take only one parameter, that is t. From this t we can write this 3 point uvw, and from here, from this two parameter uv, we can write this x, y, and z. Okay, and then you have this two things that are very important. One is the tangent to the curve, that is nothing but single differentiation, and then we have this curvature at a point. So that you have to understand from this parametric curve or a parametric curve. And parametric surface, you have to remember this equation, that is the surface normal equation, that is xu into xv, or not into xu cross xv divided by mod of xu cross xv. Okay, so that is the three things. So this you have to understand, this you have to understand, this you have to understand. This is very important, that is same thing, this or this, and then curvature, and then for this, what is the surface normal. Okay, is this thing clear to all of you, at least this parts?
So this parametric curve, what does this means? When light falls on certain object, uh, is that the thing? Is that a right understanding? Why
Parametric,
this?
yeah, parametric surface is important because you can see in the you can see in this class only that we will be talking about roof edges or steep edges, etc. So surface is very important. Okay. So in fundamental form, I will tell you two things. One is first fundamental form and second fundamental form. So first fundamental form always talks about the things on the surface, and second fundamental form how this surface is changing. Okay, so these are the two things. So that is why this parametric surface is important, and for understanding the parametric surface you have to understand what is the parametric curve. Okay, so that is the whole story.
So basically, surfaces can be of different types.
Yeah, yeah, yeah,
So
exactly.
there is 2D curve or it may be 3D also, right?
No, surface is always 3D. 2D we are only it has been written for understanding. From 2D only we move to 3D, right? Any equation we first do it in 2D and then we move into 3D. So that is why parametric curve 2D is given. But parametric surface is the main thing. And for understanding the parametric surface, you have to understand parametric curve in 3D. Okay, and parametric curve in 3D, the base of parametric curve in 3D is parametric curve in 2D. Okay, so this is the whole story.
Okay, thank you.
So this is the thing. Then we will see these things with the help of questions that will be more better clear to you. Okay, and then we have this, yeah, we have this first fundamental form and second fundamental form. Okay, so first fundamental, okay. Yeah. So first fundamental form and second fundamental form. So first fundamental form always refers to your intrinsic parameter or whatever you are see on the surface. Okay, like calculation of length. Okay, calculation of angle, calculation of length, angle. What else? Area. So this comes from this first fundamental form. Whereas second fundamental form, it shows us it is an extrinsic surface parameter. That means it shows us how this surface is changing. That means with respect to normal or tangent, etc. So that is known as second fundamental form. Okay, so second fundamental form always tells us it is an extrinsic surface parameter. It tells us how this surface is changing. But first fundamental form, it is an intrinsic surface parameter. That means it will give only the calculation on the surface. That means calculation of length, etc., etc. Okay, so this is regarding first fundamental form and second fundamental form. That is the main difference. Okay, so first fundamental form, this is how we write the first fundamental form, and this is the equation I t dot t. These are the two vectors t dot t. So yeah, this is the equation of the first fundamental form. E u dash square 2 f v dash and g v dash square. Okay, what is this E? E is xu dot xu. Xu is again nothing but this thing. Okay, xu or small xu or capital Xu, whatever you tell, same thing. So this is how we calculate E. Similarly, F is calculated by this and G is calculated by this. So this all formulas, no need to just mug up. I can just explain it with the help of questions, so that it will be better clear. And this is the equation of the second fundamental form. Second fundamental form tells us how the surface is changing. So that is why here every equation you will have normal in it. So again it is written in the same type of equation. Okay, to have a consistency. Here in place of capital E, in second fundamental form we use the small e. So small e u dash square 2f u dash v dash and then g v dash square. Okay, so this is the second fundamental form. Why second fundamental form is important, I have already told you, because it is an extrinsic surface parameter. It will tell us how the curve is changing or how the surface is changing. Okay, with the help of normal. So the normal of curvature or the normal curvature is given by the second fundamental form. Second fundamental form to be normalized by the magnitude of the tangent. Magnitude of tangent means this is the first fundamental form. So second fundamental form divided by first fundamental form will give us the normal curvature. So this formula is actually important. What is the formula of normal curvature? That is this second form divided by the first form. Okay, so this formula is important. Okay, we will solve the question there, it will be better clear. And then we have this linear map, Gaussian and mean curvature. Okay, so instead of writing this first fundamental form and second fundamental form, we can also write it in the form of linear map. So this is the linear map. This linear map is written in this form, that is small e, f, f and g, similarly capital E, f, f and g, but inverse of it. Okay, so why we are concerned about this linear map, or why this linear map is popular? Linear map is popular because once you will solve this linear map, or once you will, you can say, you will form this matrix. Okay, this is nothing but this result will come in the form of matrix. Okay, so whenever you will form this matrix and calculate the eigenvalue of it, eigenvalue or principal curvature, that is k1 and k2, the eigenvalue of it, whenever you will add the multiply the eigenvalue by this, you will get the Gaussian curvature. Okay, so this is Gaussian curvature. So first, it's very easy. First you just solve this matrix and then find the eigenvalue of it, and then multiply the eigenvalue to get the Gaussian curvature. Okay, and then to get the mean curvature, what you have to do, you have to do the half of trace of eigenvalues. That means trace is nothing but the sum of diagonal. So just do the sum of either do the sum of diagonal, or just sum of this eigenvalues and then divide it by 2, and by that you will get the this mean curvature. And this is the nothing but this eigenvalue equation. Okay, k square minus 2hk plus k. Okay, and 2h is nothing but this thing, that is the 2 into the mean curvature, and k is nothing but the but this Gaussian curvature. Okay, so by this also we can express it. Okay, so this is the thing. So linear map, why we are again, and the use of linear map, because it gives us better visibility of E and F values. Okay, and this E and F values, and by this we are getting the K1 and K2 values. K1 and K2 are nothing but the eigenvalues of this matrix. Okay, so this matrix, whenever we will solve the eigenvalues, so that is nothing but K and K1 we will get. And by this K and K1, we can see if both are negative, we will get the peak, and both are positive, we will get the pit. Okay, and there are similarly there are other like ridge, flat valley, etc. So by this K and K2, you can say the nature of the surfaces. Similarly, if you not focus on K and K2, but focus on this mean curvature and this Gaussian curvature, okay, then also you can have this eight different visible surfaces. Like h is less than 0, k is greater than 0, then you will have this peak surface. Okay, and then similarly flat surface, h equal to 0, k equals to 0, and this pit surface, the other surfaces you can see. So that is again the use of this linear mapping. Okay, so this is regarding this second fundamental form, because second fundamental form always tell us how the surface is changing. Okay, so this is the use of this second fundamental form. So is the theory clear to all of you, what I have told? First fundamental form, second fundamental form. First fundamental form, intrinsic surface parameters, that means the parameters that we can calculate on the surface, like length, area, then angle. So that is first fundamental form. Second fundamental form, it's tell us how the surface is changing, or it is known as extrinsic surface parameter. Okay, so how the surface is changing, and how the surface is changing, how we can calculate? We can calculate based on the normal, because if the surface is changing, the normal at every point will keep on changing. So that is the second fundamental form. Okay, and second fundamental form, if we divide the second fundamental form by first fundamental form, we can get the equation of the normal curvature. Okay, so this is the thing, normal curvature. And then what you can do from this first fundamental form and second fundamental form, you can form this linear mapping, and this linear mapping will give us this two different curvature. One is Gaussian curvature, and another one is mean curvature. Gaussian curvature is nothing but product of eigenvalues. Mean curvature is nothing but half of the trace of the eigenvalues. Okay, and from this two eigenvalues we can get different type, or from this Gaussian curvature or mean curvature also we can get different type of surfaces. Okay, so this is the theory. So is it clear? Oh. So from this, let's just move into the question. That will be better and that will be easy to understand. And so this is the curve xt, that is a parametric curve. You can see parametric curve because x is a function of t and t is the parameter, and xt is given by this 3t t square 2t cube, and then we are asked to calculate the curvature. Okay, calculate the curvature of the point. Okay, so how we can calculate the curvature of the point at t equals to 1, that we have to calculate. So how we can calculate? Very easy. First we can just calculate the x dash, that will be equal to 3 and 2t and 6t square. Okay, that will be x dash, and then we will calculate the x double dash t. X double dash t, 3 is a constant, that is a 0, 2 and 12t. So we have calculated x dash t and x double dash t. Now because our question is asked that t equals to 1 we have to calculate, so just put t equals to 1. So if we put t equals to 1, we will get this x dash t will be x dash 1 is given by this, x double dash 1 is given by this. So dash means first order differentiation, double dash means second order differentiation. So this is the thing, and then we can for numerator first we have to do this find out this cross product, and then we have to do the mod of it. So just do the cross product. So ijk, you write 3 to 6 and 0 to 12, and just do the cross product, and you will get this equation. Okay, 12 minus 36 and 6. Okay, you can just verify, like 24 minus 12, that is 12, and then you can verify for j and k. Okay, so this is the thing. X the numerator is coming 12 minus 36 and 6, and again mod is there, so then we have to calculate the magnitude of it. So just calculate the magnitude of it, and this is coming 6 root over 41. And then what you have to do, you have to just do the x dash t mod. So x dash t is coming this, okay, 3 to 6, and then again we have to calculate the mod of this, and mod of this is coming I think 7. Okay, mod of this is coming 7. So and then you have to do cube root. Okay, so your answer will be 6 root 41, that is the denominator, divided by 7 cube, that is 343. So this is the equation, this is the answer of the question or exercise 1. So is this thing clear how we calculated it?
Yes, this is related to 3D surface, right?
Yeah, 3D surface or 3D parametric curve, you can say.
Okay.
Okay. So any doubt regarding this? Anyone, any doubt how we have calculated x dash t in cross or cross product x double dash t mod of it divided by x dash t cube? Okay, and again mod means magnitude of x dash t in cube. Okay, so that is how we calculate the curvature of a point. So let me move on to the next question. This is the next question. Consider the following representation of a surface: x uv, y uv, and z uv. That is parametric surface. Okay, and the equation of x u is given by this. Okay, sorry, x uv is given by this f1u. This is this f1u is the complete thing, and this is g1b. Okay, so equation of x uv is given this, y uv is given like this, and z uv is given like this. Okay, so compute the surface normal, Gaussian, and mean curvature at uv equals to 0.5, 0.5. Okay, so this is the second question. So how to calculate this? So first we have this fu, that is this fu. Okay, fu, this is the fu full, this is the fu, and then we have this gv. Okay, this is the gv. Then what we will do, first step is to calculate f dash u and g dash v, and then as our question is asking at u equals to v equals to 0.5, you can see u equals to v equals to 0.5, 0.5. That is why you just whatever you have calculated, you just put u and v as 0.5. So by putting u and b as 0.5, we get this fu, gv, f dash u, and g dash v. Now what is our xu? Xu is given by fu into gv. Okay, fu into gv, that is small xu. Okay, and x dash u, sorry, capital xu is given by f dash u dot gv. Okay, f dash u into gv. That is how your xu is. We calculate this xu. Capital xv is given by this fu dot g dash v. Dot means, okay, someone, yeah, yeah, f dash u dot g dash v. So that is how you calculate this xu and xv. Okay, why we are calculating xu and xv? Because first, by this we can calculate the normal, surface normal, that is given by this formula, as I have already indicated, that is xu cross xv divided by xu cross xv mod of it. Okay, at we have to calculate at u equals to v equals to 0.5. Okay, 0.5, 0.5. So just first of all, just calculate xu and xv, and after that you perform on this. Okay, and then you can get the answer to it. Okay, so from this just multiply this f dash u and f dash v. Okay, f dash u, that is this f dash u, and g v, that is this. Okay, first you calculate this, just do the dot product. Dot product means just this element wise multiplication, that is dot product. That means 4.5 into 5, 11.75 into 1, 4.75 into 5. By that you can calculate the capital xu. Similarly xv you can calculate by this fu, that is this, into g dash v, that is this. So by this you can calculate the xv. If you have both this, just upper you just do the cross product of it, and upper numerator you do the cross product of it, denominator you have to do the take the mod of this cross product. Okay, by that you can get the surface normal equation. Okay, so that is coming this. Okay, and then what you have to do, you have to calculate the you have to calculate the Gaussian curvature and mean curvature. So to calculate the Gaussian curvature and mean curvature, these parameters are important, right? E, F, G, E, F and G. So how this E, F and G is calculated? E is calculated as this xu dot xu, F is this, G is this, and E is calculated by x u u, F is x u v, and G is x v v, and then we have to multiply dot product to this normal, surface normal, that we have just calculated. Okay, so for this xuu, this is the equation that you have to understand, that is f double dash u into gv. Xuv f dash u g dash v, xvv f u into g double dash v. Okay, so once you got this three things, and you have this normal curvature, you can get the small e, small f, and small g. And after that you can just perform this, have this linear map. Either you just simplify this, you calculate the eigenvalues, and then you calculate this. Otherwise these are the formulas that we already know. So by this also you can get the Gaussian curvature, and this is the mean curvature. Okay, so this is the thing. So the linear map is coming this, and by this the Gaussian curvature is coming this, and this mean curvature is coming this. Okay, so this is how you have to proceed. So any doubt in this?
Yeah, this Gaussian curvature and mean curvature. What is the significance of calculating this?
These are different type of curvature. Okay, so
Okay.
significance, yeah, more theory you can just read out, but these are the different type of curvature. One is normal curvature, second is this Gaussian curvature, and third is this mean curvature. Mean curvature is means you can say mean of all these points, something like that. Okay, and similarly Gaussian curvature also you can check. Okay, so this is the thing.
Okay, so mean is whatever points we calculate on the surface normal. It's mean of all those surface normal points, and
Yeah, yeah.
Gaussian.
Gaussian is this Gaussian curve. You form a Gaussian curve, and after that, I think area under the curve. Okay, so that is Gaussian curvature.
Whichever points falls under Gaussian area.
Yeah, something like that. Okay, so this
Oh,
is yeah. But most important thing is the formula. By the formula only you can get the you will get the Gaussian by on the basis of the formula only. Okay, so you would be
okay.
given the surface curves, and then you have to calculate the Gaussian curvature or the mean curvature. Okay.
Yeah, but if we know the what is this
Okay, the
about, then
theory,
it is
yeah,
easy to remember the formula. If I
yeah. The
just
theory I can include after this class. I can
uh,
include in the slide
okay,
wherever I have given you the Gaussian curvature and mean curvature. There only I will include the theory behind it. Okay.
fine. Thank
Okay.
you.
So is the question clear? How the question we have proceeded it? Any doubt regarding the question? That is most important. Any doubt? How we have proceeded it? Any doubt? So from fu how to get f dash u? It is clear, right? Just do one differentiation, that is del f by del u. Okay. Similarly, from gv to g dash v, how we have calculated, that is del g by del v. Okay. So that is why g dash v is coming 2v 1 and 0. Okay. And first this matrix is constant, so constant we do not differentiate constant, but we differentiate the variable. Okay, so variable is v, so that is why v square will become 2v, v will become 1 and 1 will become 0. Okay, so that is how we get to g dash v and f dash u. After that it is very simple. Similarly we can calculate f double dash u. So what is f double dash u? That will be 2 0 0. Similarly g double dash v, that will be 2 0 0. Okay, so this is the thing. After that you can easily perform this xuu xuv xvv, similarly xu xv, and you can get all the things that you require according to the formulas. Okay.
So this u and v, it is
Parameter.
somewhat like x parameters. Okay,
Yeah.
somewhat like x and y coordinate. Is that the case?
Yeah, and not x and y coordinate, it is parameter to x y z coordinate. Okay, parameter to x y z coordinate, that is why we write x as x uv, y will be writing y as y uv, z as z uv. And again if this u and v also has parameter t, then u is written as ut and v is written as vt. Okay.
If I want to visualize this in xy space, xyz space, how can I visualize it?
It is normal xy space, there is no difference, just we are using parametric uh, or parameters to this to get the x. Okay, so that is why x is now becoming a function of something. Okay.
Okay.
Yeah. So now there is a concept of the step and roof edges in the range images. So what is this step and roof images? So in range images, the discontinuities often occurs. Two important type of discontinuities or edges are step edges or the roof edges. Okay. So this is regarding step edge and this is regarding roof edge. Okay. So step edge, if I tell you the definition, so a step edge occurs when there is a sudden change in the depth range values between the pixel. Okay, interpretation, this happens on the object boundaries. Okay, or occluding edges where one object ends and another or the background begins. So that is step edge. Appearance in range images a sharp jump in the pixel values. So that is how we can say it is a step edge. Example, edge between a box and the wall behind it. So that is step edge. Roof edge occurs when the depth value changes gradually to a peak. Okay, depth value changes gradually to a peak or a ridge and then decreases. Here you can see here if I talk about the step. So a step edge occurs when there is a sudden change in depth. Okay, that is the range values between the adjacent pixels. So that is step. This is a roof edge. Okay, roof edge means a roof edge occurs when the depth value changes gradually to a peak and then decreases. So this is the difference between step edge and the roof edge. Interpretation of this: surface discontinuity due to curvature, often at ridges or corners of an object where two faces. Yeah. Appearance in real image: a line of the local maxima minima in the depth gradient. Okay. An example: the edge along the ridge of a roof, or the sharp fold on the corner of the cube. So that is roof edge. Okay. So again, if I talk in layman, so range images has some discontinuities or edges. Okay. So edges, there can be two type of edges. One is step edge and another one is roof edge. Step edge means when there is a sudden change in depth range values between the adjacent pixel. Roof edge means gradual change to a peak and then decrease. So that is roof edge. So by this we can understand what is a step image, what is a roof image. Example: if I just put a cube and the wall behind it, so the edge between a box and the wall behind it, that is a step edge. But if I talk about in a single cube, the corners of the cube, the edge along the ridge of a roof, or the sharp fold on the corner of a cube, that is a roof edge. So there are two type of discontinuity: step edge and the roof edge, and we can say it like this. Okay. And then these are some of the differences I have given you: step edge and roof edge. Step edge depth value, it's abrupt jump, gradual slope with a peak, occurs at the object boundary occlusion, ridge, crease or fold on the surface, gradient very high, that because it is a sudden change. Here it is a high at peak and zero at the ridge center. Okay. So this is the difference, or this is the difference between the step edges in range image and the roof edges in range images. Okay. And characteristics, again, these are not very important, but let's just discuss. So step edges are zero crossing of one principal curvature, or the Gaussian curvature, whose position changes with scale. Okay. So this constant, that is k sigma double dash by k sigma dash, that will remain roughly constant across the scale. Whereas roof edge is characterized by local maxima of the curvature and to be sought in direction of the dominant principal curvature. Okay. So here this sigma k sigma double dash and k sigma dash, it will remain constant. Okay. And sigma dash g is nothing but a Gaussian mask. Okay. Gaussian mask of scale sigma. Sigma is nothing but standard deviation. Okay. And this is the equation of the this zx is the equation of the curvature, and z sigma x is after we do the Gaussian multiplication, or after we put this Gaussian function on this on this curvature, we get this z sigma double dash x. Okay. And curvature at the point that is given by k sigma x, that is given by z sigma by 1 plus z dash sigma, or sorry, z sigma double dash by 1 plus z dash sigma 3 by 2. So that is how we get the curvature at the Gaussian smoothing. So again, better if we will just see it by an example, that will be much better clear to you. So this is a consider a 1D range profile. So this is the z1x. Okay. We have this two curve. One is this z1x, and then one is z2x. Okay. So two curves are given using the curvature formula. This is the curvature formula. Determine whether the point x equals to 0 in each profile, that is this first profile and second profile, correspond to a step edge or the roof edge. So what first you have to do, you have to first do the derivative of it. Okay. So let's just consider the case 1. This is our first curve. So that is why case 1, first curve. First derivative you have to take. So first derivative is coming this. Okay. And then again you can calculate at point x equals to 0. So that is coming this. Second derivative is coming this. Okay. And if you if you just calculate the curvature formula, curvature at point x equals to 0, that is uh, given by this formula k10. So just put the value, z double dash x will be minus 2, and your this is 1 plus z dash x. So z dash x is coming 0, so 1 plus 0 to the power 3 by 2, that will be remain 1. So your answer is coming minus 2. So it is a non-zero curvature with a peak. Okay, so that is why we can term it as a roof edge. So interpretation, if I just talk about the interpretation, so this is a roof edge, because a roof edge is identified by a local maxima or minima of the curvature along the profile. So imagine the top ridge of a roof, the surface bends there, and the curvature is high at the ridge line. Okay, so that is why we can tell it as a roof edge. Okay, but if I talk about this case 2, this is another curve, that is this curve. Again we have to do the same thing, first derivative and second derivative to get z dash x and z double dash x for this second point, for this second curvature. That is why z2 dash x and z2 double dash x, and again we will calculate the curvature, and here the curvature is coming 0. That means 0 crossing at the curvature, so that is why it is known as step edge. Okay, so step edge, because step edges are defined by 0 crossing of the curvature. Okay, but 0 crossing of the curvature, the slope changes abruptly. Okay, but slope is changing abruptly, right? What is the slope? Because this z dash 2 is coming 6, so slope is changing abruptly, but the bending is 0 at the center step. Okay, bending is 0 at the center step, so that is why we can say it as a this step edge. Okay, this is a example of a roof edge, because some curvature is coming. Okay, but here non-zero curvature is coming here, the curvature is 0. That means curvature is 0 means this value will be 0, this value will be 0, that is how curvature will be 0. So this value will be 0 means 0 crossing of the curvature. That means the curvature is not changing much. Okay, so that is why z double dash x is 0. So step edge, because step edge are defined as 0 crossing of the curvature. The slope is changing because we are getting 6, so slope is changing, but this value is not changing abruptly, or the curvature or this z double dash is not changing abruptly. Z double dash is nothing but change of z dash. So this z double dash is not changing abruptly, or the value is 0. Therefore we can say it is a step edge. Okay, so that is how we can define whether it is a roof edge or whether it is a step edge. Okay, so this is how we have said it, whether it is a roof edge or whether it is a step edge. So any doubt in this?
So in this formula, we are calculating derivative two times. First is
Yeah. So So the two-time derivative will give us the curvature formula, because curvature formula will take both the first derivative and the second derivative. Okay, z double dash x will be at the top, and at the top or at the numerator, and the denominator it is 1 plus z dash x to the power 3 by 2. Okay,
yeah.
so
So
yeah, please.
the first derivative it represents attribute like the length and the height. It is right.
Yeah.
But when we take the second derivative, it's a second order parameters.
Second derivative means, first derivative means you can say first derivative means how the tangent is changing. Second derivative means it is the how the first derivative means how the points are changing. Okay, or the tangent. Second derivative means how the tangent is changing. So that is the difference between first derivative and second derivative. And for curvature we require both first derivative as well as second derivative. Now for both these cases, first derivative will come some values. Okay, but for this step edges, the second derivative will mostly come 0. Okay, or very small. Okay, so by that we can say it is a step edge. But for this roof edge, the second derivative will also have some value. So that is why we can say it is a roof edge. Okay, So that is the difference between step edge and
Age
edge.
means typically in computer vision. Age means, is that the same age that we are referring to here?
Can you
Age
please repeat?
age detection. If we say in computer vision,
Yeah, yeah,
uh,
edge detection, but computer vision edge detection we were earlier doing regarding only 2D edge, okay, or edge in the 2D image. Okay, here we are discussing about edges in the range image. Okay, so that
okay,
is the difference. Here we are directly going to the point cloud or just the depth. Okay, there we are talking about you can say intensity values or color intensity values. So that is
hmm,
the difference.
got it. Thank you.
Okay. So by this, let me just move on to the next topic, that is segmentation into the plane via region growing. Again, it is much theory, but let's just discuss the basics of it. When we have a range image or the depth map, range image means depth map because for two half D image, right? So we are just talking about the depth map. Surfaces of the real world object often form a planar region like wall, floor, or table surfaces. So region growing method, it is a segmentation approach where we pick a seed pixel or the starting point and then we check its neighborhood pixels. And if the neighborhood pixel have similar plane properties, then we add them to make the region. The process continues until no more pixel can be added. So it grows a region corresponding to one plane in the scene. This is useful in 3D reconstruction, robotics, and object recognition. So this is the whole theory. So again, I am repeating. So what we are doing here is we are actually finding the planar regions of the depth map or the range image. Okay, so how we are finding the planar region of the depth map or the range images? First, because this is planar regions are important because this planar region can corresponding to walls or floors or table surfaces. That is why here we are most interested in finding the planar regions in the range images. So what is the theory behind it, how we approach this problem? So first we pick a seed pixel or the starting point, then what we do, we check its neighborhood pixel. If the neighborhood pixel have similar plane properties, then we add them to become region, and then we just continue the process until no more pixel can be added. By this what will happen, we can form we can the one pixel, that seed pixel, it grows to a corresponding to a one plane in the scene. Okay, so we have only started with seed pixel, but after adding all the neighborhood pixel with similar plane property, we are reaching this plane in the scene. So this is useful in 3D reconstruction or any other thing like object recognition, robot, etc. Okay, so 3D reconstruction only just focus on this. This is known as segmentation into plane via region growing. Okay, so first we are taking a seed pixel, we are checking the neighborhood pixel. If it has same planar property, we are keep on adding it, and by that we are growing a from one pixel we are growing a whole region, so whole planar region. Okay, so this is segmentation into a plane via region growing. Two important concept here or two important methodology, not methodology, terminology are here for this segmentation into plane via region growing. One is this DNP or difference of normal plane. Second is this NPS or normal plane separation. Okay, so what is this DNP or difference to normal plane? So at each pixel we can estimate a surface normal vector, a vector per okay, a vector perpendicular to the local surface. Okay, DNP measures the difference in orientation between the normal of the seed region, that the starting pixel and the normal to the candidate pixel. If DNP is small, then the pixel is likely to be the same plane. If DNP is large, the pixel belongs to a different plane. So here we are checking. First, we are again taking the seed point, and we are just checking the neighbor. If the neighbor has similar surface normal, then we are telling that both belongs to the same plane. Otherwise, we are telling it is not belonging to a same plane. So think of DNP as how much the candidate surface tilted in comparison to the current plane. If the tilt is below a certain threshold or DNP is small, we say that the pixel is likely to be the part of the same plane, otherwise the pixel will be not part of the same plane. So this is the first terminology, or the difference of normal to plane, DNP. Next we have this NPS terminology, or normal plane separation terminology. Okay, so this measures the distance of candidate pixel from the seed plane along the normal direction. So now we are talking about distance of candidate pixel from the seed plane along the normal direction. So in other words, it is how far the candidate point lies below the plane of equation, okay, or the plane of the seed point, okay, how far the candidate point lies above or below the seed point. If the distance is small, again same thing, we will consider a threshold. If the distance is less than threshold, then the point belongs to the same plane, otherwise point is not belonging to the same plane. Okay, so think of NPS as how far away is the candidate point from the current plane surface. Okay, so two terminology. One is DNP, difference of normal to the plane. So that tells us how much the candidate surface tilted compared to the current plane. And second is NPS, that is normal plane separation. It tells us how far is the candidate point from the current plane surface. So in reason growing, I have told in this third point that similar plane property. So how we can say the candidate point or the neighbor point has the same plane property as the seed pixel, that we that we understand by this two terminology, DNP and NPS. If DNP is coming lesser than threshold, then orientation are similar. NPS is coming lesser than threshold, point lies close to the plane. This ensure the same flat plane, and we get grouped together in this region growing process. Okay, so this is the whole concept. So is it clear what I have told? So let me again repeat. Here we are talking about segmentation into a plane via growing region growing. So what we do is, segmentation into plane via region growing. Why is it essential? And essential because when we are talking about range images, these planar regions are important, because it can just tell you about whether it is a wall, floor, or table surface. So that is why planar regions are important. Okay, and it can be used in any 3D reconstruction. So how we proceed this problem? First we take a seed pixel, okay, and then we check the neighborhood pixel. Also neighborhood pixel is also called candidate pixel. And for this candidate pixel, we check if the candidate pixel has similar plane property with our seed point. If it has similar plane property, then we add it to the seed point, and by we keep on adding this neighbor if it has similar plane property, and this one point or the seed point grows into a region. So that is known as region growing. Now what about the similar plane property? How we determine the similar plane property? We determine the similar plane property by this two thing. One is the DNP, that is difference of normal to plane, which tells us how much the candidate surface or candidate point is tilted to the current or the seed point. And second is NPS, or the normal plane separation. It tells us how far away the candidate point is to the seed point. If both are lesser than threshold, DNP is less than threshold, NPS is also less than threshold, then we say that the point has similar plane property, and we will use the candidate point for this region growing. Otherwise we will not use that candidate point for region growing. So this is the whole theory behind this segmentation into plane via region growing. So is this clear to all of you?
So if pixel belongs to different surfaces, how can we identify that? Means segmentation is only applicable if pixel represents the same surface. Is that the case?
Can you please repeat?
No, what I'm saying is
Yeah.
we first need to identify whether the pixel belongs to same surface or different surface. That and
Yeah, yeah,
then
yeah, yeah.
we, then we segment that area. But what if the pixel belongs to different surface?
Then it will have different segmentation color. Okay, for example, for this surface I am using a different color, this surface I am using a different color, so something like that. So see, we are the whole topic is segmentation into plane via region growing. So we are segmenting via same plane. Okay, different plane we are not segmenting. So that is segmentation into plane via region growing. Okay, for that, if whether the candidate pixel, we have two different pixel. One is the seed pixel from where we are starting, and then we have a candidate pixel, that is the neighborhood to the seed pixel. Okay, and if the candidate pixel has same planar property, then we just same planar property, then we just add this point for this region growing. Otherwise we do not add this point for region growing to form a planar region. Okay, region growing means planar region growing. Okay, so this is how we do it. And two properties are there. One is two terminology are there to say if the candidate point has same properties or not. One is DNP and second is NPS. Okay, if both are lesser than threshold, then same planar property. Otherwise, not the same planar property. Okay, so that is how we do it.
Thank you.
Yeah, so we have this different digital neighborhood plane. So this is again you can just read out, but yeah, this is important. So different plane configuration. Okay, so generally we have this three principal plane. One is this x, you can say xy plane, yz plane, and zx plane. Okay, so three principal plane, and then we have this diagonal plane. So we have this six diagonal planes. Okay, so that this is the DNP in base configuration. Again, this is taken from some paper. Okay, so not very important, but again questions can come from this, that how many digital neighborhood planes are there. So for that you have to write it like three principal plane and six diagonal planes for DNP. NPS also I have told you all this threshold, etc. So this again, this all these things are taken from some paper, so not very important, but this you should always remember, that DNP configuration, this digital neighborhood plane, we can classify all the neighborhood plane into this three principal plane and six diagonal planes, that means 9 planes. Okay, so this only you have to just remember. Other, it has been taken from some paper, so you can just check the paper if you are interested. Okay, otherwise the theory that I have told you here, so this is sufficient. Okay, and then let me move to the next thing. Algorithm also you can check. So same thing, NPS as well as DNP is also important. Here only NPS is given, but NPS as well as DNP both are important. Here I think they have taken for a same DNP. First they have see if the pixel belong to the same DNP or not. After that they have computed with this NPS. Okay, so that is how they have done in the algorithm. But I have told you, if you have to grow the region, you have to see both the DNP as well as NPS. Okay, if DNP is lesser than certain threshold and NPS is lesser than something threshold, then only you can add those candidate pixel to your seed pixel and grow it into a region. Okay, so that is how you do it. And then we have this last thing known as this registration of range data. Again, it is a theory is given. Registration of range data is the process of aligning two or more range images of the same object or scene into a common coordinate system. Okay, so that is the definition. So again I am repeating, registration of range data is the process of aligning two or more range images of the same object. Okay, or the scene into a common coordinate system. Okay, so a range image or a point cloud is captured from specific viewpoint, that is by a laser scanner, lidar, or the depth camera. Since one viewpoint only covers a part of the object, we need to combine multiple viewpoints to reconstruct the whole 3D shape. So registration finds the rigid transformation that best aligns the partial scan. Okay, so very easy, like we are taking this range images from different viewpoint, and then we are adding it to form the complete reconstruction. So that is registration of the range data. And to add it, we have to use this rigid transformation, that is rotation as well as this translation. Okay, so again there are some assumption, etc., that is given, you can read it. But our computational problem is to estimation of rotation and translation parameter. That means how we can register two different viewpoints. We can register two different viewpoints, like we have this two scan, one is scan A and scan B. Okay, so so this A and B represent the same physical surface, same physical surface location. Okay, so for that, to compute rigid transformation from scan B, so from scan A to scan B, what we have to do, we have to do this transformation. Okay, so that is rotation and this is translation. Okay, because rigid transformation, it is a two-step process. One is rotation and second is translation. So R into PA, okay, P is nothing but, I think, position of the scan A. So rotation into PA plus translation to give the position of the scan B. Okay, R is the rotation matrix, T is the translation vector. Okay, and then what we will see, yeah, first we will do it and then we will minimize the error. Okay, iteratively refine the alignment to minimize distance between the corresponding points. Output align scan in a common coordinate frame. So again, if I just repeat the step, so first step is two range images. Okay, say scan A and scan B. Second is feature extraction, that is detect geometric feature, corner, edges, surface patches, or use all points. Okay, and then corresponding matching, we have to do the matching. Okay, find pairs of point A and B that represents the same physical location. Okay, and then what we do this transformation estimation, that is compute the rigid transformation. So PB can be written as rotation into point A plus translation, and then we just do the error minimization. We have to minimize the error, and then align output align scan in common coordinate frame. Okay, if I just say it by the formula, so this mi and di are two corresponding points in the two scans. Okay, so di equals to r into mi plus t into vi is some noise. Okay, so this just you can just ignore. So what will be the error? Error will be nothing but this di minus rmi plus t. So that this error we have to minimize, and this error, if we can minimize it, okay, minimize it, so we can calculate, minimize it and just get it to 0. By that we can calculate what is the rotation and what is the translation. So this is the whole theory. Again, these things won't come much in your formula, these formulas won't come much in your exam, but this is how you do it. Okay, so just minimize the error. For minimizing the error, what you do, you just do this thing. Okay, del E by del T will be equal to 0. By this you calculate what is your two things are important. Okay, what is your T and what is your D. Okay, so by this you can get your if you get the R as rotation and translation, you can get how you should align your two different scan and then combine it to form a single scan. Okay, so one of the algorithm is this iterative closest point or ICP registration algorithm. It compute the initial registration parameter r naught and t naught, then initialize the error e to e naught, and then it repeats the following step until the error converges or becomes small. Converges means there is no decrease of error further. Further, that is convergence. Okay, convergence means like this. Okay, that means with steps, like if this is the step and this is the error e, so convergence means like this. That means your error might not get to 0, but it will converge. That means no further reduction of the error. So that is convergence. So we have to find out r naught, r and t such that this error converges. Okay, so after that we apply the transformation, compute the closest pair between the source and target seed, recompute registration parameter, and error of fitting. Again, you can check all this. All this are theory. So again, I am not going very deep, but this is the whole thing. So generally you just have to remember what is registration. So registration of range data, process of aligning two or more range images of the same object or the same scene into a common coordinate system. So that is registration. Okay, so registration finds the rigid transformation, that is r and t, that best align the partial scan. Okay, these are the two things you have to remember. This two, if you just remember, you can get the idea of the whole thing. Okay, and rigid transformation, so basically we have to find what is the rotation and what is the translation to align the scans into one coordinate system. Okay, so that is the whole theory behind it. Okay, again I am not going very deep because all this are theory, and definitely this formula won't come in your exam, because this is just this is an iterative process to just minimize the error and to compute R and T. Okay, so this is regarding the registration of the range images. Okay, and then let's just move into the question. So topic on which this week 9 assignment question are based, so you can just read it. These are the topic on which the assignment questions are based. Okay, so let's start the first question. Consider the set of parametric equation xt and yt. X as a function of t is given and y as a function of t is given, that is 2D parametric curve. Okay, compute the tangent vector x dash t and y dash t. Okay, so what will be the x dash t? X dash t will be 2t plus 3, right? Y dash t will be 4t 4t plus 0. Okay, because minus 1 is a constant, so 0. So the x dash t is 2t plus 3, y dash t is 4t, and at t equals to 1, what will be the x dash t? You have to calculate. At t equals to 1, what is the y dash t? You have to calculate. Okay, so just see the steps. It is very easy, just I have told you. Just calculate the x dash t, that is 2t plus 3, and y dash t, that is 4t, and just put t equals to 1. It is coming, x dash 1 is coming 5 and y dash 1 is coming 4. So your answer will be 5 comma 4, or option A is your answer. Okay, so is it clear regarding tangent, how to calculate tangent of a 2D parametric curve? Clear, right? Okay, nice. Now regarding this question number 2, which of the following is true about Microsoft Kinect sensor? Okay, so that Microsoft Kinect sensor uses infrared laser light with speckle pattern. This is Microsoft Kinect sensor. This is nothing but, this is an example of your structured light. Okay, so we have discussed about three active image ranging. Okay, one is time of flight, second is triangulation method, and third is this structured light. So this Microsoft Kinect sensor is the third thing, that is structured light example. Okay, so it uses infrared laser light with speckle pattern. B, if a point is at the higher depth from the sensor, it looks more blurry. Option C, uses the principle of structured light. Option D, all of the above. So any guesses for this?
D.
Yeah, D, right? All of the above, right? Because this is of course true, I have already told you. Yeah, the source which it will use, because there will be, as it is again, structure light is again a type of this triangulation method only. So in triangulation method, three things are there. One is the source, second is the object, third is the camera. Here the source will not emit one, you can say one spot or one ray, but rather it will emit a pattern. Okay, so that is why it uses spectral infrared light with speckle pattern. Regarding second, if a point is at higher depth from the sensor, it will look blurry, because the structure light pattern becomes less distant as the depth increases. Points farther from the sensor appears blurrier. So definitely, because when the points will be farther from the sensor, it will appear blurrer. Okay, so that is the thing. And see, it is definitely it is an example of a principle structured light. Okay, principle of structured light. So option D is the correct answer. So I hope it is clear to all of you. So let me move on to the third question. Consider the coefficient of first fundamental form. Capital E, capital F and capital G are given, and the coefficient of second fundamental form, small e, small f and small g are given. Compute the Gaussian curvature K. Okay, so what we can do, either we can just form the linear map, and then what we can do, just form the linear map. After forming the linear map, we just find out the eigenvalues, and after the finding out the eigenvalue, the Gaussian curvature is nothing but the multiplication of the eigenvalue, or the multiplication of eigenvalue is nothing but the determinant of the linear map. So just find out the linear map and just find the determinant, then also we can compute the Gaussian curvature. Otherwise, you just go with this method. Okay. So this method, k is given by this. That is determinant of this second first inverse is nothing but your linear map only, and determinant of linear map will give you the k value. Now we know the property of determinant. If we have determinant of two matrix, that is determinant AB determinant AB will be written as determinant A into determinant B, that we can write. So determinant A into determinant B, here B is inverse, that is why we have written determinant second divided by determinant 1. Okay, so that this thing, okay, determinant AB is written like this. Now we can easily find this is the first fundamental form, so we can easily find the determinant of this, that is 15 minus 1, that is 14, and here it is 9 minus 49, that is minus of 40. Okay, so we have this determinant of second, that is minus of 40, determinant of first is nothing but 14, right? And then we can calculate the k. Okay, so Gaussian curvature can be given by this. Okay, so this is one trick. Another trick is to go with the long method, that is first you just compute the because this is what is our this linear map is nothing but second form into first inverse of first form. Okay, this is the equation of the linear map. So what we have to do, this is inverse. Okay, minus of 1, inverse, so inverse of the first, and this is the second form. This is the inverse of the first, and this is the second form. So second form we already got, this is the second form. We just what we have to do, just find out the inverse of the first form and form a linear map. So your linear map is coming this. Okay, this is coming your linear map. Yeah, this is coming your linear map, and once you get the linear map, you either calculate the eigenvalue, or better you can as here you have been also no need to calculate eigenvalue also if you don't want. So that is another thing, because to calculate this thing G or K to calculate this better to calculate the eigenvalue. You just calculate the eigenvalue, or just form this characteristics equation. What is characteristic equation? A minus lambda I equals to 0. This is your A matrix, and lambda I is nothing but your this 1001, that is this identity matrix. So just A minus lambda I, mod of A minus lambda I equals to 0, that will give you the eigenvalue. Form this equation. Okay, and when you form this equation, this part will be trace, and this part will be determinant, and determinant only will give you the Gaussian curvature. So by this also you can see minus 20/7 is coming. So this also you can see this determinant is coming minus 20/7. So this is also the Gaussian curvature. And if you are going by the linear map process, you can also calculate the mean curvature. Otherwise, if you are going by this process, you cannot compute the mean curvature. Okay, so this is the whole theory behind it. Okay, so this is the thing. So is it clear to all of you?
Sir, I have one
Sir,
more.
what is
Yeah, please.
Sir, E and F G value is if we came negative, it should not be negative. I think so, right? Small e, small f, and G will be always positive value. There
Always
is anything will be
positive.
there.
Always positive. Why so?
I'm asked because when I have to solve the problem in videos, I'll get all the value will be negative in what exercise problem.
So
But
yeah, it
in
can be
this one,
negative.
they'll put a positive.
No,
Exercise number 2, I think so, sir.
no, I don't think so. It can be negative. E and F, small e f g or capital E f g, it can be negative.
Can be negative. But I got all value will be negative, but answer what SAR will be solved it all to be in positive. That's why I'm asking.
No, I don't think so. This thing should be happen.
Actually, it is in the exercise problem only.
Okay,
Exercise
so
2, I think.
yeah, so I can solve it. I can solve
Okay.
it and give you the solutions. Okay.
Yeah.
But you all understand, right? What is the why? This is the first method. Like, let me again tell you. This is the first method. Okay. If you are only given to calculate k, you can just do this and just get the answer. But best thing is to get the linear map. Why we are getting the linear map? If we from the linear map, if we just form the characteristic equation, we will get the both. Okay, we will get both. That is Gaussian curvature as well as the mean curvature. That is why best thing is to form the linear map. If you can form the linear map, then you can get both. Okay, that is both the Gaussian curvature as well as the mean curvature. Otherwise, if you are just given the to find the Gaussian curvature, you can easily escape with this. Okay, just do this and you can easily escape with this. Okay, so this is the thing. So I hope this is question is clear to all of you. Clear, right? Any step, any doubt? This is an important question. This type of question will definitely come.
Sir, is there any other formula is available for calculate the mean curvature like Gaussian curvature?
Yeah, mean curvature, there is also a formula. I will show you. Okay, but better to not memorize the formula. What I will suggest, if you can, it's good. If you cannot, I have already shown you. Like gosh, mean curvature also I have shown you the formula. I think, right? Yeah, this is the formula for this for your mean curvature. This is the formula of Gaussian curvature. So if you can
Okay, okay, okay.
memorize this, it is good. Otherwise, always form a linear map. Once you form a linear map, after linear map, you have to form the characteristic equation. Characteristic equation is nothing but a minus lambda I, mod of a minus lambda I will be equal to 0. So if you just form the characteristic equation, you can get both. That is Gaussian curvature as well as this mean curvature. Okay, so that is more better. This is the equation of your this is the characteristic equation, and by this characteristic equation you can get both. The last or the c your equation is ax square plus bx plus c will be equal to 0, or x square minus b by a plus c by a plus b by a plus c by a plus b by a x plus c by a will be equal to 0. So c by a is nothing but your k. Okay, that is the this Gaussian curvature. Okay, so better just form a linear map, and from linear map you can get both. Okay, so that is how you can solve. Okay, let's move on to the next question. Choose the correct option. 8 illumination levels are used in binary encoding. N patterns must be projected in order to encode 2n stripes in space encoding. Every encoded point in the binary encoding is identified by the sequence of occurrence it receives. Every decoded point in the space encoding is identified by sequence of intensity that it receives. So let me show you. So definitely 8 illumination levels are not used in binary encoding. Whenever we are talking about binary encoding, we use 2 illumination level, either 0 or 1. Okay, not 8. Okay, next is correct, that is n patterns must be projected in order to encode 2 to the power n stripes in space encoding, because with n binary pattern you can uniquely encode 2n regions of stripes. Third is also correct, that is every encoded point in a C is also correct, every encoded point in a binary encoding is identified by the sequence of occurrence that it receives. So that is also true, that each point is identified by its binary code sequence. And D, every decoded point, not decoded point but encoded point. Okay, every decoded point in a space encoding is identified by a sequence of intensity that it receives. No, not every decoded point but every encoded point in binary encoding is identified by sequence of occurrence it receives. So option B as well as option C is the correct answer. This is totally theoretical question regarding your coding for this structured light. Okay, so this is the thing. So this is complete theory, you can just read it, and this is how it shows. Okay, and let's move on to again the next question, that is consider a hyperbolic paraboloid represents as a parametric surface xuv as u, v and uv, with u equals to this 3t square plus 2t, v equals to 2t plus 1. Compute all of the first fundamental form coefficient at t equals to 2. Okay, so how you proceed this? You have to proceed like this. You have to first calculate xu and then xv. What is xu? Xu is nothing but del x by del u, that is xu. And what is xv? Xv is nothing but del x by del v. Okay, that is xv. Once you got xu and xv, your e can be calculated like this, f can be calculated like this, and g can be calculated like this. Okay, so very easy. Once you got this, 1 plus v square. Now v at t equals to 2 you can calculate, that is 5, and v square is nothing but 25. Okay, so yeah, v square is nothing but 25, so e you will get 26. Similarly you can get the value of f and you can get the value of g. So option D is your correct answer. So 26, 80 and 257 is correct. 26, 80 and 257, yeah. So option D is your correct answer. That is none of this. Okay. So that is how you have to solve it. You can just refer to the exercise question. Very much similar question. So it is kind of same thing. Okay. So by this you can create.
Just a question I have here.
Yeah.
So here, this surface is represented by only one x. It's not means additional y uv is not here. Is there any specific reason that it can be represented only by x uv?
Xu is nothing but it is a vector. Like x, you have seen this, right? Xu, like xyz. If I write xyz, okay, so I can write xyz z as x vector, right? By point, you just remember point in etc, we write it as x vector, right? Or the x vector. Okay, similarly uv and uv we can write it as xv. Okay, so this is nothing but you can say the kind of vector, because it is taking all these three things. So uv and uv. Okay, so this is nothing but vector. Okay, that
It's
is
a
what.
different representation. So how it can be mapped to the general space? Like generally we represent any point in xyz space. So there must be some mechanism wherein we can map it to uv space also.
UV space.
Maybe because I haven't understood this. What is the difference, like when we represent a point in XYZ space, or when we represent the same point or the parametric surface in this XUV form? Like, is
Yeah,
that
so basically this xyz, xyz you can say x yeah, xyz you can x is a function of uv, y is a function of uv, z is a function of u and va. Okay, so these are function of the parameters u and v. Okay, so that
hmm.
is how it is representing. Like not a sim, like how I can explain you this, like this is x is formed by two parameter u and v. So okay, so this x is a function of u and v. Similarly this y is also a function of u and v. Similarly this z is also a function of u and v, and then this u and v also is a function of t. Okay, so these are functions. Okay, like
Okay.
x can vary from something to something by
So to
one
derive
parameter.
X value, I need to calculate the function
Yeah, yeah, yeah,
X.
yeah,
Okay,
yeah.
got it.
To calculate this x value you have to this x value or this x position value, this is a function of uv. Similarly this y position value, this is a function of uv. This z position value, this is also a function of uv, and this u and v also is a function of t. Okay, so this
Where
is the
T is the tangent.
no, t is a parameter. T is not
T
the
is a
tangent. T is a
parameter,
parameter.
and what
U
does
and
that
V.
mean?
T is a parameter for U and V. U and V is a parameter for this X, Y, and Z. Okay.
Okay, got it.
So I hope the rest of the question is clear to all of you. How we have done it. Okay, nice. Which of the following statements are not true for detection of edges in range images? Roof edge points detected from zero crossing of the Gaussian curvature. Step edge points are detected from zero crossing of the Gaussian curvature. Step edge points are detected by extreme dominant principal curvature of the corresponding curvature corresponding to its direction. Roof edge points are detected by extrema of dominant principal curvature corresponding to its direction. So any guesses for this? Very easy, right? Roof edge points are detected by from zero crossing of the Gaussian curvature, that is false. Okay. Step edge point are detected by zero crossing of the Gaussian curvature, and roof edge points are detected by extrema of dominant principal curvature. Okay. So option B as well as option D is your correct answer. Okay. And option A is not your correct option, as well as option C is also not your correct option. Okay. So that is the definition. That step edge points are detected from zero crossing of the Gaussian curvature. Step edge sudden depth discontinuity often correspond to sharp changes in surface shape. Okay. So at this location, the Gaussian curvature typically changes sign zero crossing of the Gaussian curvature by identify them. Okay. And this is regarding roof edge points are detected by extrema of dominant principal curvature corresponding to its direction. So option B as well as option D is your correct answer. But here it has been told which are not true for detection. Okay. Which are not true. Okay. So we have to tell the reverse of it. So option A as well option C is correct here. Okay. So this is the thing. Again, it is a pure theoretical question. So just you have to understand this. And then question number 7, consider the coefficient of the first fundamental form, that is capital EFG as given, second fundamental form small EFG as given, compute the mean curvature. So mean curvature either you can just compute by this formula, you have all this EFG and capital EFG is given, so you can just put all these values and you will get the mean curvature, or better to form a linear map. That I always suggest, just form a linear map, and this is how you form a linear map, that is first inverse. So this is how we write the linear map. So just second you already have, second matrix you already have, and first matrix what you have to do, you have to calculate the inverse of it, and after that you will get the linear map matrix. Okay. After getting the linear map matrix, it is very easy. That is the trace of k divided by 2 will be giving you the mean curvature. Okay. Trace is nothing but the sum of diagonal, so just make the sum of diagonal, and then what you do, you just do the half of it, and that will give you the mean curvature, and that will give you the mean curvature. And how you can get the Gaussian curvature, it is very easy. Determinant of it will give you the Gaussian curvature. Okay. So very easy. So that this way you can do it. Otherwise, again, if you will form that characteristic equation also, again same thing. Okay. Same thing, the that the middle term will be minus b by a, so minus b by 2a will give you the trace. Okay. And last term, that is c by a, will give you the Gaussian curvature. Okay. So that way also you can do. So either you go with the first way or you go with the second way. Okay. Anything that you like, either you go with this or you go with this. Okay. If you will go with this part, so here you will calculate, you can calculate both. That is mean curvature also and Gaussian curvature also. If you go with the formula, then you can just calculate for either for the mean curvature or the Gaussian curvature. That means it has different formulas. Okay. For this mean curvature and Gaussian curvature. Okay. So that is how you can solve the question. So is it clear to all of you what I have told? Clear, right? Yes. Which of the following are example of active imaging? Time of flight sensor, triangulation based sensor, structured light, or the stereo imaging? So this is a very simple question. I hope everyone knows this. Which of the following are example of active imaging? First slide, come on. Which one of the following is not not an example of active imaging? Which one of the following is not an example of active imaging or passive imaging? Am I audible?
Stereo imaging.
Yeah, stereo imaging is not an example. So other three are example of active imaging. Okay. So this is very simple. This is just a pure theoretical question that has been given to you. So active imaging, you can just read out that is sensor projected energy. Passive imaging, sensor only observe the ambient light. Okay. So this is not an example. Other three are example of, sorry, not this. Other three are example of this active range imaging. Okay. So time of flight, triangulation based sensor, and structured light. Okay. So this is the thing. Again a pure theoretical question. So A, B, and C are the correct answer. Question number 9. Which of the following uses laser radar LADAR sensor? Time of flight, triangulation based sensor, or option C, stereo imaging, or option D, structured light? So any guesses for this? Time of flight, right? Time of flight only you will use your lidar or lidar, whatever you say. Okay. Lidar is light detection and ranging. This laser detection and ranging is lidar. Okay. So time of flight only will use the lidar or lidar. Okay. Other triangulation and etc. they do not usually use this. So triangulation based sensor use geometry with projected light, not laser radar. Stereo imaging, passive method, no laser. And structured light, it uses laser but not lidar. Okay. So uses projected pattern, so it uses laser. Okay, not laser radar. Laser, it uses only laser but not laser radar or lidar or whatever you can say. Okay. So lidar means you will have one sensor only, and the source will go to the object. It will reflect it back to the object. So that is lidar or lidar. Okay. But this triangulation method, it has this triangulation concept. One is your source, one is this object, and one is this camera. Okay. So for both this triangulation as well as structured light. Okay. So this operates on this principle. So here you required camera and you required a source, not lidar. Lidar means same source and same receiver. So that is lidar or lidar. Okay. So that is why time of flight only uses your lidar or lidar. Okay. Other imaging like structured light or this triangulation based sensor, they can use laser but not lidar. Okay. So this is the thing. Stereo imaging, it generally don't use any of this. It uses the concept of two different cameras. Okay. So this is regarding question number 9. So is it clear to all of you what I have told? Clear, right? Nice. Now choose the correct option regarding digital neighborhood plane DNP for a 3D neighborhood of a point P. Number of planes are principal planes are 3. Number of diagonal planes are 6. Total number of digital neighborhood planes are 9. Total number of digital neighborhood planes are 8. So any guesses which one is incorrect? Option D is incorrect, right? Option A is right. We have 3 principal planes, XY, YZ and ZX, and we have this 6 diagonal planes. So total number of planes 3 plus 6 equals to 9. Okay. So option D is the wrong answer. That is total number of digital neighborhood planes are not 8 but 9. Okay. So this is the whole theory behind it. That we have 3 principal planes, XY plane, YZ and ZX, and we have this 6 diagonal planes. Okay. 6 diagonal planes that passes diagonally through the 3D grid neighborhood. Okay. 6 diagonal planes. And total 3 plus 6, that is equal to 9 total planes, total 9 DNP planes. So option D is wrong. Okay. 8 is wrong. So option A, option B as well as option C are the correct answer. So here you can get more theoretical question rather than numerical question. Numerical question always comes from that first fundamental form, second fundamental form, or regarding this your surface parametric curve, or this no, 2D or the 3D parametric curve. Okay, so this is the questions regarding your assignment, similar question regarding your assignment 9. Okay, so any doubt regarding today's class?
No, sir.
So let me just show you this.
See, the concepts are related to 3D reconstruction or 3D LiDAR, or
Yeah,
combination of both.
3D. Can you
3D
please?
LiDAR or 3D reconstruction.
Yeah. 3D reconstruction. All these concepts are related to 3D reconstruction. Okay, because range images will give you a point cloud, and from that point cloud you can just do from this registration, or from this detecting edges, etc. You can do all that detection in the 3D space, or detection in the point cloud, or this registration, alignment, etc. that you can do. Okay, so let me show you one code. Yeah. So these are the different codes. You can just open this codes and see. So let me show you this code. Okay, what type of range image and how it looks like. So let me show you. Yeah, so this data is extracted from this TUM RGBD data set, and you can just see. Yeah, so this is a depth map. Okay, this I hope, yeah, here the main image is not given, but yeah, this is the depth map. Okay, so this is the depth map, or this is you can say a range image. So only range image means you can get for each pixel you can get this distances. Okay, so this is the depth map or the range image. Okay, and this are the step edges. You can see these are the step edges, and these are the roof edges. Okay, so step edges step edges means your different type of discontinuity, and roof edges means different type of discontinuity. Okay, so this is the regarding how we can get step edges and roof edges. So from this code you can just see this code, and from this code you can understand how you can get the step edges and the roof edges. Okay, so this is one code. So let me show you the 3D point cloud. Okay, so that will be more interesting to you. So this data is from RGBD image, not a range image. Range image is just a depth image. Okay, so this data set is from RGBD image. Okay, so where is the, yeah, so this is the RGB image, and this is the depth map, and together this is the RGBD image. Okay, so RGB image, and this is a D image, or the depth image. So together, if I combine together, that is known as this depth image, and this is the point cloud. Okay, so you can just rotate or etc. So this is a 3D space. Okay, so this is a complete point cloud. This codes and etc. I have given to you, so you can just copy the code to your drive. Something here it has been written, whenever you will open it, something here it would be written like copy to drive. Just copy the code to your drive, and you can see all this. Okay, so this you can just check out, and let me show you other things like a region growing, that does not, let me show you this. Okay, so other things are important on my region growing step. Yeah, this already I have told you. So just show you one registration thing. So how the registration and before and after registration. So yeah, so see, this is before registration. That means the things are taking from two different viewpoints. Okay, red is from different viewpoint, and blue is from different viewpoint. After registration, this is regarding after registration. Okay, so all the values are aligned. Okay, so this green means all are aligned. Okay, so and this you can say these are some residual errors. So this is regarding registration. Okay, and point cloud, I think point cloud it has not been shown, I think, point cloud. So this is regarding registration. So this also you can open this. Okay, and these are the codes. Okay, so this is regarding this, and I think someone is asking, when I started the class, someone is asking question number 5, fifth of the previous
Yes, sir. Yes, sir.
yeah,
Question number 5.
Yes. So this is, yeah. So this, what is the doubt in this? What is doubt in this? Can you please clarify what is the doubt in this? Am I audible?
Sir, yes, sir. That another problem. Maximally
Okay, so
saturated point.
question number
That
six.
problem.
Yeah, question number
Sixth
six.
problem. Sixth problem.
Yeah. So what is the doubt in this? Values
Sir,
values are coming different. That is what you are telling.
yes, final value, sir. GR plus WQ equal to, we get the minus
And it's
0.0116.
saturated point. How we have to get 0.28, 208 and 0.286. How we have to
Yes,
get this
yes,
value?
yes.
That's how we have it also.
So 0.
GR and WQ we got it.
Yeah, yeah, yeah. So this
That
is,
answer.
yeah. So this is the thing, no?
This answer, how can we solve it? We don't know. That's why we
So minus
actually I also say
minus
same doubt.
0.016 divided by minus 0.039. What it is coming? I don't have calculator now. Someone can calculate and tell me.
Wait, wait, sir. I will calculate.
Okay, sir.
16 divided by 39. You just do this. 16 divided by 39.
Yes, yes.
How much it is coming?
0.410.
0.41.
Okay, 0.41 it is coming. Okay, so I think it is
Uh,
given wrong here. Okay, so I can just I think the point given wrong here. So yeah, that I can clarify. I can,
okay,
okay.
okay.
So
But
whatever
procedure
the
is
answer,
nothing but
yeah,
minus zero
uh,
point
0
zero
point,
one six divided by minus 0.039.
and this, how much this is coming? 22 divided by 39.
0.56.
0.56. So 0.41 and 0.56 will be your answer.
Actually, half of the value here we have to get. I think so.
Half of the
Uh,
values are given. Okay.
yeah, I think so. Divided by 2, 0.28 will be given coming over here.
Can you do this? Do this for me. 0.7 divided by 4. Yeah, 7 divided by 4 is
7 divided by 4 is
1.7.
0.7. 0.
Sorry, not
Actually,
7 divided by 26. Sorry, 7 divided
so
by 26. How much it is coming?
0.2692, I think so.
I don't know why the answers are given like this. Okay, so whatever the answer
That's
will come, no, I don't think it is half of any, because here 0.286 is also not half of this. So whatever value you are getting, that will be, I think, answer. Okay.
you have to
Okay,
divide it
okay.
by first value and by third value and second value by third
No,
value. Is it right?
this is nothing but scale, right? And this
Yeah,
is the
okay.
inhomogeneous
Yeah,
yeah,
okay.
inhomogeneous coordinate. So that is
Okay.
why this is homogeneous coordinate. So to get the value in inhomogeneous coordinate, we divide it by scale. So this third is
Okay.
the scale. So just
Okay.
divide 16 by, or minus 0.016 by minus 0.039. So you will get this, whatever value it will come, and
Yeah.
minus 0.022 divided by 0.039. Okay.
Okay.
So any
That's
other
why actually.
yeah, any
That's
other
why I
points?
also have a same doubt. I have
Okay,
to
okay.
clarify it.
So
Yeah.
what about this? We have another
Exercise correct,
question.
sir. Exercise one correct.
Exercise 1 is correct. So there I
Yes,
think there
yes,
is
yes.
some problem. Okay. Exercise 1 is correct, right?
Yes,
Like
yes, yes, yes.
what? Yeah, this is the thing. Okay. So it is it 127 divided by 490? Can anyone check? 127 divided by
Yes, yes,
490?
correct, sir. That one correct.
Correct. Yeah. So there I think, yeah,
0.25.
yeah. So there I think there is some problem. Okay. So I think,
Same problem also, sir, is solved in lecture.
okay. Exercise 1 is correct. Here the values are coming wrong. Okay, no problem. So just I will just rectify this. Okay, I will rectify this.
Okay, okay. No issues.
Okay. So you got the method, right? How we calculate this? That is important. Everyone got
That's
this,
why
right?
that's why we have to ask again. We have a doubt. That's why I
Okay,
have
okay. I
asked.
will just do this calculation again and just do this. Okay.
Okay, sir. Thank you.
So by this I am ending the session for today. Okay, and we will meet on the next Friday, or I might take one class on Tuesday. I will let you all know, because I think the next to next Friday is, I think, this vacation, Durga Puja vacation, etc. So that is why I am thinking of taking your next Friday class to next Tuesday, and next to next Friday class to next Friday. Okay, that I am thinking. Okay, if that will be the case, you will all get informed by mail. Okay.
Okay, sir.
Okay, so
Okay.
okay, so by this I am ending the session for today. Okay, so bye
Okay.
everyone.
Thank you.